let y1, y2, yn be continuous random variables with the joint probability density function. This is the abbreviation I am using, with the joint probability density function f of y. So basically we can explicitly write y1, y2, yn, y1, y2, yn. So this is joint probability density function, and the marginal probability density function of yi be f of yi. Okay. So this is the assumption that they have joined. So if the random variables y1, y2, yn are said to be independent random variables if, this is the definition, their joint probability mass function, here probability mass function we talked when we discussed the discrete cases. Here, because we are considering continuous cases, the independent random variables, if the joint probability density function, we will talk about the joint probability density function in case of continuous cases. This is just I am again writing as explicitly the notation. It should not be it should be clearly understood. It can be written as their product. So similarly to the discrete cases, or in bivariate continuous random variable cases also we discussed. So this is f of y1, y1, f of y2, y2, f of yn, yn. So in simplified notation we can say that f of this joint probability density function is product of their marginals. So here we have to be careful that this has to be true for all values of, so we can either say that small y tilde yn belongs to Rn, or we can say for all yi belongs to R for I is equal to 1 to n. So if these conditions are satisfied, so this condition is satisfied, so then we say that this y1, y2, yn are independent random variables, continuous. For the continuous cases we have to, so it is similar definition we discussed for the discrete cases. So when it is independent, so it is a product of their random variables. For continuous cases, product of their probability density. For discrete cases, it is product of their probability mass functions. Joint probability mass functions can be represented by the product of their marginal probability mass function. For continuous cases, the joint probability density function can be represented by the product of their marginal probability density functions whenever they are independent. So here also, if you know the marginal probability density function, and also if you assume or we know that the random variables are independent, so then we can find their joint probability density function. So let us discuss one example. Suppose let us consider normal random variables. So let y1, y2, yn be normal random variable, normally okay. So let be normal distributed random variables, or we can just let yn be continuous random variable, be continuous random variable with each yi has some normal distribution, mean mu I, variance sigma square. So note that we denote normal distribution like this. We discussed this normal distribution mean mu I, variance sigma square. So for simplicity, let us assume that sigma square is suppose 1. For let us consider it is like this. So for simplicity only, sigma square also we can take any values. So now because here also mu I we are considering, if you consider same mu like 1 some value, so it will be identically distributed random variable. But here we are considering different mu I for different I, different mean. So it is not identically distributed, they are not identically distributed random variables, they are different random variables. So if so, then what is the probability density function of yi is given by, probability density function of yi is given by, so because it is a normally distributed random variable, f of yi it is 1 by root 2 pi. So sigma is here 1 e to the power of minus yi minus mu I whole square by 2, sigma square is 1, where yi can take any value between minus infinity to plus infinity for I is equal to, so this is density function of every y1, y2, yn, it is represented in this notation yi for I is equal to 1 to n. Now if y1, y2, yn are independent random variables, the joint probability density function of yn is given by, if they are independent random variables, then we can find the their joint probability density function. So how? Because we know that if they are independent random variables, then by definition the joint probability density function can be represented by their product of their marginal. So here this advantage is that we can find the joint probability density function. So y of y, say, so let us explicitly write, so to understand it clearly, y1, y2, yn. So then what is this? This is because they are independent, so it will be true for all y1, y2, yn, f of y2, y2, then f of yn, yn. So this is equal to so 1 by, so f of y1, y1, if we put I is equal to 1, then 1 by root 2 pi e to the power of minus y1 minus mu 1 whole square by 2 multiplied with 1 by root 2 pi e to the power of minus y2 by minus mu 2 by whole square by 2. So 1 by root 2 pi e to the power of minus yn minus mu n whole square by 2. So then we can simplify because it is 2 pi. So 2 pi whole to the power, it is in the denominator, so it is minus n by 2 e to the power of, we can write minus summation of yi minus mu I whole square by 2 or 1 by 2 it is. So this is the joint probability for whenever yi minus mu to plus infinity for I is equal to 1 to n. So this is the joint probability density function. So note that if they are not independent, so this will not be the joint probability density function. So that we will discuss how multivariate some of the distribution function we know how the joint probability density function looks like in case of they are not independent. In case of y1, y2, yn are multivariate probability density function, how we can find. So how some of the random variable we know, so we will discuss that. So but in that case here we assume that they are independent. So by independent definition here we discussed, and then using the independent definition we found the joint probability density function using their marginal probability density functions. Now we will discuss the moments of the multivariate random variables. So we have already discussed for bivariate cases, it is very straightforward extension from the bivariate to the multivariate cases for the moments. So let us discuss first how we can define the mean. So mean of a random variable, let x, x1, x2, xn be a multivariate random variable. So first let us consider discrete random variable. So multivariate, let us consider multivariate discrete random variable, with the joint probability mass function. So some joint probability mass function. So we have discussed if they are independent, it can be found using their marginals, but if it is not independent, we have to know the joint probability mass function. Let us assume if in general cases p x1 x2 xn be the joint probability mass function. Now with the joint probability mass function that is given here. Now what will be the mean? So in general case, let us consider, let y is a random variable, it is a function x1 x2 xn. So where g is a function from Rn to R. So any function you can consider Rn to Rm in general cases, but here for simplicity let us consider this is a transformation of random variable. We will discuss in this next chapter the transformation of random variable some of the next weeks. So here it is like a function of random variable we discussed. So how we can find using expected values of y, how we can find using the joint probability mass function of x1 x2 xn. So expected value of y, expected value of g x1 x2 xn, it is, the definition is that it will be sum of all the possible values it can take g x1 x2 xn with their probability. So let us write here. So this is sum of the all the possible values. Suppose sum of this is xn, xn minus 1, x1, this g x1 x2 xn, this value can take with the probability x1 x2 xn, x1 x2 xn. So these are the sum of the all possible values of that x1 can take, x2 can take, like that, and then what is the values of g x1 x2 xn multiplied with their probability. So this is the general definition. Now we can use the general definition to find all other like moments. So suppose we are finding the first order moments. So the mean of, suppose let us find mean of yi is given by, so we denote by notation, suppose mu y. So mu y high, so it is the ith random variable expected values of xi. So here whenever we are writing expected value of xi, so that means you are considering your g x1 x2 xn function is nothing but xi. So if you put this g x1 x2 xn equal to xi here in this general formula, so then you can find the expected value of xi. So that's why this general we have written. So this will be nothing but, this will be summation all values of xn, all possible values of xn minus 1, x1. So g of x1 x2 xn, what is this? This value it is nothing but the xi only, the ith value, and this is not probability of x1 x2 xn, x1 x2 xn. So this will be. Now if you just separate out the ith value, and suppose we because xi is not dependent of other values x1 xn minus 1 xn, so then we just take the sum outside xi ith value. So here it is a problem is that, so this is actually we can take xi is a variable here, and then it is actually taking this value of some in this range of rxi actually, and then it is xi, and then take the sum of other value. So then sum of xn minus 1. So basically xi can be also xn, in that case we will not take sum of this, just it is a generally we are writing, and the other, so here actually that's why we should write in this way. So this is xi minus 1, xi plus 1, because ith variable we are not taking the sum here, and then x1, this x1 x2 xn x1 x2 xn. So remember that what is this value. So we are taking the sum of this joint probability mass function of all the variables except xi. So in that case you can remember that we will get a marginal probability mass function. So marginal probability mass function of which random variable? Marginal probability mass function of xi we will get, because we are not taking the sum of, for continuous cases like we did continuous cases, for if we don't take the integration of ith value, then we will get the marginal. Similarly here for discrete cases, if you don't do the sum of the those random variables, but the other random variable are taking sum, so then we will get the marginal probability mass function. So then this is nothing but summation of all these values xi it is taking in rxi, because of this confusion here also xi, this is also xi. Actually the sum of the all possible values xi, we will take the sum. And what is this value? This is nothing but the marginal probability mass function of xi. This is the usual definition of the mu I, actually you can remember. So this is the general definition, so that we can actually from the general definition we can find the our the univariate cases definition, because this general definition can be used for any other moments also. So now similarly we can find the variance also. So variance sigma square is variance of suppose xi. So variance of xi, we need this definition, you can remember, this is xi minus mu I whole square. Now if you consider how we can find this expected value. So if you consider this g x1 x2 xn, in that case in this general formula, so if you consider g of x1 x2 xn, this is xi minus mu I whole square, so then you can find the formula there. So here you can put this g1 x2, so this is nothing but summation of the all values it can take xn, all values can take xn minus 1 x1. So then this is xi minus mu I whole square, then p of x1 x2 xn, then x1 x2 xn. So now see that this ith value variable similarly we can separate out, and then it can be represented again summation of all value xi can take in the rxi, and then xi minus mu I whole square, then this is nothing but the marginal probability mass function of xi, very similar to the previous computation we did. So that's why I am not repeating these things again. So these things like here xi minus mu I whole square, it will be separated out here, and then remaining part will be nothing but the marginal probability mass function. So always we can simplify in this way, we are not saying, but here we can simplify because it is a more complex situation, multivariate random variable we are dealing. So this is the variance. So but it can be represented, we know that this can be represented like summation of xi rxi. So xi square px xi of xi minus summation of xi rxi into xi into px of xi, probability pxi of xi whole square. So that actually this formula, so this is mu 2 dash minus mu 1 dash whole square, that is nothing but expected values of xi square minus expected values of xi whole square. So this is actually, this is we can say mu 2 dash for the ith variable, how we can represent like mu 2 dash I minus mu 1 dash ith variable whole square. So that for any I, for I is equal to 1 to n. So that is the formula we have already, we know already, we have computed some of the numerical example, you can remember these things, we are not doing again. So this is, you can go back to some of the other videos, that how this can be, this general definition of the variance can be represented this by simplified form, and most of the time we use this simplified form computing the variance. Now because it is a multivariate random variables, we are more interested about how they are related each other. Suppose we are considering these two random variables, suppose xi and xj. So these two random variables, how they are related. So that for bivariate cases we discussed it. So then we define it as like a covariance of xi and xj. So covariance of xi xj, it is denoted, we denote x sigma ij. So it is by definition, this is nothing but it is, we discussed xi minus mu I and xj minus mu j. So for any I is equal to, for I and j belongs to 1 to n. So note that I and j can be equal also. So in that case it will be xi minus mu I whole square, and in that case this will be nothing but the sigma I square variance. So whenever I not equal to j, we get the covariance. So so it can be also simplified in this way. This is expected values of xi xj minus mu I into mu j. So this is the covariance. And also in bivariate cases we discussed that the covariance is not unitless. So we cannot compare two different, suppose, set of random variables with respect to their covariance, how the value, we cannot say that they are more correlated or they are more they are associated each other than the other two random variables, we cannot say. So that's why we need some quantity that can be comparable. So in that case we defined actually it is defined the correlation coefficient. So the correlation coefficient between the I and j, the correlation coefficient, between xi and xj is defined by so we can denote by sigma rho ij between, that is one correlation between xi and xj. So it is defined by covariance between xi and xj by variance of xi and root over of variance of xj. So if they are like sum of the any units, so it is actually become unitless because we are dividing also. So then this is simplified notation. Covariance of xi is nothing but sigma ij, and this is root over of sigma I and root over of sigma ij. So this is sigma I into sigma j for any I for I j belongs to 1 to n. So if I not equal to j, then we get the correlation coefficient between two different random variable. If I is equal to j, so this is nothing but 1 because they are the same random variable. Covariance between the variance sigma I square by sigma I root over sigma I into sigma I, this become 1. So for I not equal to j, we get the correlation coefficient between two different random variable xi and xj. So here you can see that. So those things are discussed here, covariance between zi and zj. So basically here we did not use the same variable. So this is just a change of variable in this slide we kept here. So zi zj instead of xi xj we used, and rho ij we discussed. This is covariance sigma ij by sigma I into sigma j. So this is the covariance and correlation coefficient between two random variables. For bivariate cases we already discussed, because we are taking two random variables at a time. So it is nothing but the bivariate cases we already discussed. So suppose how they are related, suppose correlation coefficient xi and xj. So this is the one random variable and another random variable xj. So if you know the correlation coefficient sigma ij, so depending upon the random variable sigma ij, so if it is close to 1, so then this data scatter plot will be looks like. So if yxj is increasing, then yj also will increasing. So it will be like a straight line. So most of the time it will be around a straight line. Now if rho ij is equal to close to the -1, so that we already discussed that this value rho ij correlation coefficient is always less than equal to 1 and it is greater than equal to -1. So that can be shown by Cauchy-Schwarz inequality. We are not going in details about that, but it is just to mention that correlation coefficient has very significant implication in analyzing the their relationship between two random variables. So the correlation coefficient will be always between -1 and +1, and this will be, if it is close to 1, that means they are related as a straight line. So we say a linear relationship. This is -1. If it is -1, that is also a linear relationship, but it will be negatively correlated, we say. So that means this data will be looks like this. So this case basically rho ij is close to 1, and this case rho ij is close to -1. Now if the data does not show any this kind of relationship, straight line relationship, maybe there may be other relationship, like it is a circle, or like sometimes it is increasing, sometimes decreasing, not like linear type of any relationship, then this correlation coefficient will not be close to 1 or -1, this will be close to 0. So, if these values are close to 0, so then there will not be any linear relationship. These two random variables do not show any linear relationship between their values. So, this is the concept of the moments. So, we just discussed first order moment and the second order moment, because it is a multivariate random variable. So, it may be complicated to discuss more higher order moments. So, here we discussed first order moment and second order moment like sigma square, and then we discussed how to relate themselves, like correlation, they are how they are correlated. To relate that, we discussed the covariance and the correlation coefficient.